based on what model? Just a moment. Yeah, based on what model you believe in, the rates change slightly, but we expect to detect dozens of binary neutron star mergers per year, and also about 550 on-axis GRBs. That's about 50 short GRBs and 500 long GRBs per year. On board, we can localize it to about 10 degrees, which is great because in a few pointings, a telescope like ZTF can cover that entire area. With on-ground processing, the localization is expected to improve. Of course, if the burst is brighter, we will do much better localization. It is the only mission that will be able to give the broadband spectrum that includes soft spectrum. So for GRBs or for any other high energy burst, typically what happens with a mission like SWIFT is that the satellite has to slew and point its soft X-ray telescope to that location for getting more detailed soft spectra. But Daksha will actually have open all-sky detectors for that as well. It has excellent capabilities for hard X-ray polarimetry. And then another fun thing is Daksha will allow us to look under the rug. So if you look at the LVK sensitivities, the threshold for what is considered as a gravitational wave detection is set by all sky all the time false alarm rate. But if you have an electromagnetic detection, then it gives you the direction of the source and it gives you the time window in which the merger must have happened. That allows you to significantly reduce your threshold because it lowers your false alarm rate. You have to find any event that you find in GW data has to be consistent with this. And we did a bit of estimation on this, and it will allow us to almost double the binary neutron star detection rate with gravitational wave networks. And in general, this opens up a huge discovery space, especially with these subthreshold sources, but also more broadly with the reduced false alarm, with the increased sensitivity itself, it gives us a huge leap. So there's a question in the chat, what will be the sensitivity compared to other telescopes? I'll come to that in just a bit. So what other missions are out there right now? The new missions which are coming up are SWARM and GECAM. So SWARM is a French-Chinese mission, which is expected to be launched this year sometime. And GECAM, they already launched GECAM A and B. One of them failed, the other works. They have launched GECAM C, which is a lower sensitivity thing. So China is launching satellite after satellite in order to cover this. Conceptually, GECAM is very similar to Daksha, but sensitivity-wise, it is lower. There are also a large number of CubeSat teams. So here are a few. There are some concepts, some have been launched. So GRB Alpha, Camelot, Burst Cube have already been launched. Hermes Pathfinder has been launched. But all of these are much, much lower sensitive area. And the goal in these missions is that you launch dozens or maybe even hundreds of such small satellites. So for those unfamiliar with the jargon, CubeSat is typically a 1U unit is something like this. So this is a cube which is 10 centimeters on a side. So this would be a 6U unit, which is 10 by 20 by 30 centimeters. So they have very limited sensitivity. Okay, so here is the slide I promised comparing these different missions. So I have not put COMPTEL here, but here are effective area plots of various missions. Let me see if I can just zoom in here to show this a bit better. Sorry, I can just zoom it like this to show you this plot better. Okay, so this is 1 MeV and this is the Daksha high energy detector sensitivity. For comparison, this is the sodium iodide detectors of Fermi. This is the SWARM gamma ray monitor. And this here is the Fermi BGO detectors. So the sensitivity is about a factor of 2 higher as compared to any of those. So I hope that answers your question. And this table here shows a comparison of a bunch of missions, including Theseus, which unfortunately has been cancelled already. But also it has SWARM, Eclairs, Fermi, Swift, and GECAM. So different parameters are given here, but what I'd like to draw your attention to is this volumetric, how much volume can we probe for say 170817 like events. And you can see that Daksha does a much better job than anything else. So it's about a factor of 13 better than Swift BAT and about a factor of 5 or 6 better than Fermi GBM in terms of how many 170817 like events we can detect. Okay, so that is a big advantage in favor of this mission. I would take a small detour here to address what else can Daksha do. So what are our broader science goals? If you want to go into details, just scan this QR code or note down these archive numbers. This is where we have discussed the mission specs and the science case in detail. There are also more papers that will be coming up soon. The polarization paper we expect to submit by the end of this month. But let me give you at a glance version of this. This slide is too dense, so let me spread it out instead. So we have a large variety of science cases that we want to address with this mission. Relativistic transients is the first one. We have already been talking about electromagnetic counterparts to gravitational wave sources, where we have the highest sensitivity among all satellites. But for GRB studies in general, this is the only satellite that will give soft prompt emission. And also, thanks to the very high sensitivity, while detecting faint GRBs is fun, we can do great science by doing time resolved spectroscopy of the brighter GRBs. And that is because with so much sensitivity, we can break our data into small time segment bins. And that will still give us enough SNR to do spectroscopy. So instead of fitting an averaged function for the entire spectrum, we can now start seeing how spectral parameters actually varied with time. In terms of GRB polarization, the current record holders are AstroSat, CZTI, and Polar. And the GRB polarization abilities for Daksha are better than any of these missions. Then the next set of science cases is to deal with compact objects in general, where we could be studying SGRs and magnetar flares, searching for high energy counterparts to FRBs. As you all know, there is a large uncertainty over what exactly FRB emission sources are, and there are several models which do predict high energy emission. We will be able to monitor accreting X-ray pulsars. So Fermi GBM has been doing a great job at this, and we have much higher sensitivity. So we did simulations and we found that any source that Fermi can detect, Daksha can detect it extremely easily. We can also study various other elements. So Earth Sun system, quite cool result is that there is gamma ray radiation that is associated with lightning. And these are called terrestrial gamma ray flashes. There have been a few dedicated missions that have been launched to study these TGFs, but Daksha actually has higher sensitivity than even those dedicated missions for detecting such things. We will be able to do solar flare studies, and even monitoring the Earth's atmosphere and atmospheric response to space weather is something that can be followed up. When you have a high sensitivity mission, other interesting science cases pop up too. Surud found an interesting case where by studying GRBs that are detected jointly by both satellites, we can look for signs of microlensing and actually use that to probe primordial black holes, low mass primordial black holes, and probe or possibly rule out a phase space that hasn't been probed by other missions so far. We can also study persistent sources with Earth occultation, novae, and other slow transients, and so on. What's the overall status? Daksha is being built with IIT Bombay as the lead, but jointly with a lot of other institutes involved: PRL, TIFR, Ayuka, RRI, ISRO, and the science team is spread over even more institutes. And we actually have a proof of concept ready. So this is our detector board. It's populated, tested, working. We have actually labs in IIT, TIFR, and PRL at all places. We are working copies of this board. So we are about to submit a closure report to ISRO. So ISRO had given us seed funding to show that this is actually feasible. And that part is now accomplished. So on the basis of that, we can go ahead and now tell them that this is ready, and ISRO will now evaluate the full mission for approval. And I will close with that. So if you want to know more about Daksha, go to this website. Oh, I just looked at the clock and realized that I've been speaking too fast. So I'm done well ahead of time, only 40 minutes instead of 50. I hope that's okay, Gopal.
Oh, that's perfect. We will have questions, so and that will be great. Yeah. Okay. Let's give a big round of applause to Varun for this amazing mission. So, questions, comments from younger colleagues first. Wait. Yeah, and also Zoom, there are a few. Varun, can you answer to the questions in the chat straight away?
I see only one question in the chat
Okay.
from Ramiz Muhammad, which I answered when I showed that plot. I don't
Okay.
see any other questions in the Zoom chat.
Okay, sure. Okay, so then, yeah, Avinash.
Hi, I have a question regarding pulsar timing array with the gamma ray millisecond pulsars. So
Okay.
there have been recently one paper by Fermi. So can Daksha also we can do a similar thing with better sensitivity?
So the timing resolution of Daksha is a microsecond, and we will be able to get absolute timing accuracy of about a millisecond should be quite straightforward to get. What I understand is that the pulsars that Fermi is talking about are actually emitting in MEV to GeV range, whereas in our sensitivity range, they are much fainter. So that is why we will be able to see fewer of those sources. That said, there is nothing, we haven't explored this in great detail, and there is nothing preventing us from doing that. So, if you or anyone else here is interested in probing it, then I'll be happy to work with you to figure out what our sensitivity is and what can be done on that front.
Okay, thank you.
I think there were a few other questions. I saw somebody raising. No. Okay. Yeah, then Sriram.
Thank you. Hi, Varun. Thank you for a wonderful talk. I had 3 questions. You talked about GW190814, and you talked about the masses being 2.6 solar masses and 23.2 solar masses. You couldn't see it in the optical because they were too far away. The same arguments applied as you.
Probably too far away, yes. So if you let me go back to this slide with all the listing. So this is the event, right? 190814 BV. And you can see that the distance, this is the third column here, and the distance is 6 times higher. So the median distance itself. Okay, so the flux is going to be 36 times lower. That's about 3 or 4 magnitudes fainter than 170817. The area was small. We did search to much deeper limits than 170817, and we didn't find anything, unfortunately.
Okay, I understand. A completely different question. You talked about high energy observations. Do they allow you to localize the source in the sky easily?
Yes, so we can localize typically to about, so with Daksha, we localize to about 10 degrees for a faint source. As the source becomes brighter, it is just inversely proportional to flux. So if you take a typical GR bead that is detected by, say, Fermi today, we can localize that to a degree probably. And 10 degrees radius is few hundred square degrees area. That sounds like a lot, but with wide field ground based, see, once we know that right now, here's the problem. If you look at, say, O4 predictions, we are looking at probably few candidates per week. Now, to follow up one sky area of, say, 1,000 square degrees, I have to spend an entire night of a telescope on it. So if you want EM collaborations to follow these up in great detail, you are talking of essentially shutting shop and doing only this full time. And of course, that's not going to happen. Now, on the other hand, if we see electromagnetic radiation, and then we go to these telescopes and say, look, this is not a black hole merger, right? This emitted photons, we know this is there. Then you can afford to make a stronger case and spend more time and effort in following up. And then tiling a few hundred square degrees is quite achievable with current technology.
Okay. And the last question related to, Surhut's proposal for observing primordial black holes using microlensing. What mass range are we talking about?
If I remember correctly, this is 10 raised to minus 11 to minus 14 Earth masses. But I might be butchering that badly enough that Surun might want to strangle me. What I can tell you instead is Surud has a grad student working on this, and she's written up a paper which should get submitted soon. So let me get back. Actually, wait, I can do better than that. since we have the luxury of having some time, let me tell you exactly what we can do. Yes, so 10 raised to minus 11 to minus 16 solar masses, which is pretty much not probed so far. The interesting thing here is that the size scale of this is smaller than optical wavelengths. So you can't study these with optical light at all. You need high energy radiation to be able to probe these range.
Okay, I understand. Thank you. Thank you.
Coming back to your second question, by the way, there is one more part. The localization that I've been talking about is a single satellite localization, which is what it will happen for the majority of the events. If we have a detection with two satellites, okay, a part of the sky, the satellite. So if I have Earth here and one satellite here, one here, then this mid plane is visible to both satellites, right? This part is hidden for this one, this part is hidden. So about 30% of the events will be detected by both. And there we can actually now triangulate. We can use the same LIGO-like idea of the delta T between the two satellites to get a narrow arc. Now there is another proposed NASA mission called Moonbeam, which is a slightly lower sensitivity, factor of 2 actually, lower sensitivity than Daksha, but they are going to go into a highly elliptical orbit, up to 1.3 times the distance to the moon. So we are taking up a joint study with them, saying that if Moonbeam plus Daksha or Moonbeam plus both Daksha detect an event, how well can we localize that? And that should easily come to a sub-degree field of view. When a telescope like, say, the Growth India telescope can easily observe that area and just look for counterparts.
I understand.
So,
Thank you, Varun.
welcome.
Further questions, comments?
Hi, so I have a very naive question. So when you are saying that the high energy detection actually favors neutron star, that is why it is so.
Because there were photons, you can't have it with black holes. That's
Okay. So immediately we can actually predict the surface magnetic field or so.
No. It's simply that, okay, so there are ways in which black hole mergers can cause some electromagnetic counterparts. They typically come from scenarios like having a black hole merger in the disk of an AGN, where the merger disrupts the gas in the disk, and that gives rise to optical flaring or something like that. So this happens at lower energies and at longer time scales. So if you have, we do not have any theoretical way of having black hole mergers generate any X-ray or gamma ray emission at short time scales.
Okay.
So if you have X-ray gamma ray emission at all, then it means that it has to have been emitted by a neutron star. It does not directly depend on the magnetic field. There are indirect implications. I'm not sure if they will be observable, strong enough to be observable.
Okay. And your slide number 10, the mass gap you have shown.
Yeah.
So all those purple compact objects are like, what are they?
Okay, so this okay, I jumped through this figure as I was speeding through my entire talk. For if you take any event, let's say this event, which was actually retracted, then on this gray line you see two blobs here. So the size of this circles is telling you the probability that this was a binary neutron star event versus a terrestrial event. Okay, so if you take something which is, say, this one, okay, I'm pointing out to retracted events because it's just easier to follow with that gray line. Then this was classified as a mass gap event, which meant that at least one of the objects in it was between 3 to 5 solar masses.
Okay.
If both were above 5, it was called, so the classification used by LIGO is was on one of my slides. Let me jump out and look for it. Where did that go? Here, right? So below 3 solar masses is a neutron star, 3 to 5 solar masses is mass gap, and above 5 is black hole. The reason for this is if you look at all the black hole masses that have been measured with, say, X-ray studies and stuff so on, we have never found a black hole that is lower than about 5 solar masses. Error bars extend downward. Okay.
Hmm.
We don't have a fundamental physics reason as to why you cannot have something like a 3.5 solar mass black hole, or for that matter, a 10 raised to minus 11 solar mass black hole. Okay. But the fact remains that observationally, we haven't seen black holes in this range.
Hmm.
Observationally, the heaviest neutron star is actually sitting here at 2.1 solar masses.
Hmm.
But there we are theoretically saying that, okay, up to 3 solar masses, depending on equation of state, we can have a neutron star. But this region, we have not seen compact objects in this region observationally at all. So there might be an astrophysical reason. For example, if you have to form a heavier black hole, then it may have effects on the way your supernova explodes, and it may actually cause more fallback, resulting in black holes always getting, so if you have a certain type of supernova explosion, you leave behind a neutron star. Maybe if you go into a territory which is large enough where the core was heavy enough to make a black hole, you also get more fallback. So that instead of that black hole being just above the neutron star black hole boundary, it ends up becoming much heavier. So there is plausibly a astrophysical reason here, but it is just observationally empty space, and that's why it's called the mass gap region.
Hmm. So here, this 2.59, we are calling it neutron star.
No, this is mass gap.
Okay. That's
Sorry, no. This is neutron star. This is neutron star. Yes, this is
so
moving down
we
into
are
the mass.
confirmed it is neutron star.
Sorry.
Okay, that's my question. Okay.
No. So there is no confirmation that that's actually a neutron star. It's the chirp mass is much more accurately determined. The mass ratio is a problem, even though it's unequal mass. So then that's the error bar issues working in. Varun, thank you very much for a fantastic talk. I have a bunch of questions. Is that all right?
Yeah, of course.
So I've been a bit confused. You in one of your slides you said 170817 is actually a bright event, even though we know the fluence is much lower. So in what sense did you say it's a very bright event? I'm a bit got confused.
Okay, so if all events had the same optical emission as 170817, okay, so what we did was that we use a tool called sim survey. Okay, I'll give you a little bit of behind the scenes. So we have a package in which we can inject kilonovae with various models into the sky, and then we simulate our observation strategies and say, would we have found a counterpart? Okay. And so you take, say, one of the events from O3, you take its localization volume, you throw in thousands of sources of kilonovae, and you say you tile it as ZTF actually observed that area, and you say, okay, these fraction of them were found and these were the ones not found. Okay. And based on the fact that despite doing detailed follow-ups for about a dozen or so events, we didn't see anything. It allows us to put constraints on kilonova models.
Right.
So one of the models we took said that every source was exactly the same as 170817. So 170817 had a peak absolute magnitude of about minus 16 or something like that. And if that was the case, then what would have happened? And the answer is that we should have detected something. So clearly all cannot have been the same absolute magnitude as 170817.
Okay, thank you. So this is the kind of a follow-up comment on that. So some of my colleagues in Seoul National University, they are trying to come up with something called 7DT. I kind of briefly mentioned this to you, if I'm not mistaken. So what they're trying to do is that they're going to have a spectral survey in 3 days. It's kind of a it's not a it's essentially optical wavelength, but a narrow band. So that should be, they are exclusively searching for kilonovae, and combined with this will have important implication, right? I mean,
yes.
Irrespective of whether you see it in LIGO or not.
Right.
So,
yes.
So this is something maybe you guys should talk to
So
each other.
that is the other thing which was done here. So this second paper, what we did was that independent of LIGO, we said that here is what we think overall theoretically kilonovae should evolve as a function of time. And then we went back and looked at all of our data saying how many such candidates have we ever seen? And right now, I think we found one. We're
Yes.
not strong enough to claim it a kilonova, but we couldn't rule it out either. And on the basis of that, we then put an upper limit saying that if kilonovae do this, then how many neutron star mergers could there be in space? So that was kind of work done on that front
Okay.
without
Okay.
relying on GWs.
Okay. And I have there was something I was noting it down. Give me a second. Oh, Shantanu.
But you can ask
I have to go back to it.
okay. So if you ask the question in where GW17087 has not been seen, okay, which wavelength bands, okay, so I can think of two. You can correct me if I'm wrong. It has not been seen at millimeter waves. It has not been seen in TV gamma rays. So now obviously this GRB was very far away, so probably it wouldn't have been
So,
seen in TV gamma
I
rays.
think,
So
yeah, so TeV, I know it was not seen. I'm not very sure about millimeter waves. I know it was detected in sub-mm. I know it was detected in centimeter waves. So if it was not detected in millimeters, it might just have been because
yeah,
people didn't bother.
gigahertz. I'm talking about gigahertz.
Gigahertz detection was
But
gigahertz.
were they detections?
Yeah. Lot of JVLA detections. In fact,
JVLA
one
is
of the
still, I think,
postdocs said, yeah, JVLA goes down to gigahertz.
yeah, okay. Okay, so anyhow, so what are the prospects for detecting TV gamma ray counterparts and in the
I
near
would
future?
personally, I wouldn't bet on it. And that is because even if you look at just GRBs themselves, right, with a few thousand GRBs known to date, we have one or maybe two detected in TEVs. So you need to be incredibly close and incredibly bright to get TeV emission. Another problem that comes in at high energies in general is that so first is that it is hard to create high energy photons. And second is each photon carries so much energy that for a given flux level, you get extremely few photons. They're very related, but not quite the same factors. So as a result, you are going to get extremely few photons per square centimeter on Earth from any of these events. And that makes it rather unlikely to be detected in those energies. That is also part of the reason why Daksha sensitivity, we don't bother too much beyond an MeV. Unlike Fermi, which was meant to be also a gamma ray space telescope for studying steady sources, here our focus is just on the transients, and it's hard to get GeV transient emission from a lot of GRBs. They're obtained for a few, of course. TeV, it's not GeV is not as bad a scenario as TeV is, but for search, the KeV to MEV range seems to be the best.
Okay. Yeah, I mean, so just a follow up of that, you mentioned about that prompt emission and the soft spectra, the possibility, right? That will be that will be fairly unique, right? I haven't even many of the soft gamma ray bursts, right? Where short hard gamma ray bursts, where they have suspected the kilonova and all that, right? With X-rays. So those are fairly uncertain, but your statement is that this will be, you'll have several.
So I can give several examples here. 17017 itself, there are hints of there being a soft thermal component in the prompt emission, but Fermi's sensitivity cuts off at 8 keV, so it's not quite enough to measure that. With classical GRBs, there have been studies which indicate that there could be a soft break in the spectrum, and it's modeled only as a break because no mission has sensitivity enough in those energy ranges to actually be able to fit it. If you look at the band spectrum itself, which is the typical model used to fit GRB spectra, there have been some studies which show that if you actually do time resolved, then you can start fitting more spectral models, more detailed physical models, and the average of them over time ends up looking like a band spectrum.
Okay.
So being able to detect those in prompt emission is going to be quite important. From a kilonova perspective, the kilonova strictly is the optical IR emission from this, but from a neutron star merger perspective, another thing which is important is that the most plausible thing right now is that there is some sort of a cocoon being formed and there's a shock created inside that which is breaking out, followed possibly by a structured jet and so on. So when you see the shock breakout, there's still going to be some optical depth beyond it. And it is possible, not very likely, but just possible that you could actually even constrain the NH column density by doing soft X-ray spectral measurements. So that's another interesting prospect. So you'll be able to measure exactly where you start seeing the X-ray gamma ray photons from the source.
Yeah, that will be amazing, especially, I mean, but there are doubts about the cocoon scenario, right? I mean, but it doesn't matter.
So let's see, there are doubts about whether the full-fledged cocoon as such exists, but the big picture model, if you look at it, the fact that material has to be ejected, has to form some kind of a cloud, and that's why I said possibly a structured jet, possibly a cocoon, but
Yes.
then the final, the cloud is forming before the impact, if you want to call it, and the impact is what is creating a shock. And then you are seeing a shock emission, possibly a shock breakout and everything, right? That's how you explain the delay between 170817 and the gamma rays. So that part is not really in doubt.
Yeah, I mean, precisely. I mean, maybe eventually, very careful those things. I mean, whether you can actually argue whether there's a black hole formed or not, eventually. That'd be an interesting thing to think about too.
Yes.
Great.
Yes.
So, further, any more questions? Yeah, go ahead.
Yeah.
So I have a question. You have showed various, what is the expected magnitude in optical and other bands for some of the gravitational wave detections, right? So how does it vary with the inclination angle?
No, so this is a ultra simplistic model. Okay, just for showing comparison, we assume that everything is isotropic and same as 170870.
Okay.
So this is extremely simplified. If you want to do a more detailed thing, then here is one example of it. This one. Okay, so the green line here is my ultra simplistic model. Everything is exactly 170870. When I start throwing in inclination, for example, then this is a cocoon model, but there is another paper in prep actually where we are probing this for a variety of structured jet models. So in high energy, the variation is sometimes modeled as a Gaussian jet with a certain sigma, which is few degrees, or as a power law fall off as a function of angle. In optical, the variation is not quite as high. It is within an order of magnitude. In X-rays, gamma rays, it can be a few orders of magnitude from the peak jet to outside. And also, depending on whether you are seeing on this thing as a polar or a equatorial aligned merger, that also changes the nature of the kilonova. In the equatorial region, you get what is called a red kilonova because you have more ejecta in the equatorial plane. So radiation is getting absorbed, reprocessed, and re-emitted at longer wavelengths. Whereas if you are looking at it along the polar angles, then there was less ejecta to begin with, and the jet created by the merger will also plow out a path for you. So the net combination is that you will actually see bluer emission on the polar sides.
Okay. Sorry, I just forgot. Yeah. Okay. So there are cosmic accelerations, right? So can the neutron star mergers be one of the source of those?
Possibly. I don't think they're believed to be a major source, but I'm sure they could be a source. I'm not sure.
From the gravitational wave, what do you say? From the template itself, can we say what might be the inclination angle, or do we need some additional?
So there is quite some. So you can measure angle from the gravitational wave signal, but there is quite a bit of degeneracy there. And electromagnetic observations can actually help better rule that out. And also, if I remember correctly, getting the distance which you can get from electromagnetic measurements, that also helps in breaking a bunch of these degeneracies within GW data.
Yeah, I mean, especially black hole neutron star, because they are unequal masses, the higher modes are possible. So that actually kind of feeds back onto the inclination again. So that's the reason one of those events are much better localized because they could get the higher, not just the the
Okay.
dropper. So you go beyond that unequal mass. And so the inclination also comes to help because additional, yes. This one more question. So
It's a very broad question. Because we have such a small sample size, especially with the GW and EM counterparts at once, how are you dealing with this not being like a biased selection of sources? Because we are planning various missions, we are planning EM counterparts in the future. How are we sure that this is not a very small sample size? We're looking for the nature might be doing other things which we might not have seen.
So that's a great question. The first answer is we are astronomers, so we always work with one data point. But a more serious version of it is that no, we are actually being aware of this. So, for example, this other work that I talked about, which is something in prep, let me give you a glimpse of it. If I have a slide here. Yeah. So here, what I've done is I've considered 8 different models from different groups, which account for 8 different models of emission from neutron star mergers. Okay, all of these have been scaled to allow 170817. So they are all consistent. And then we have done our rate calculations on the basis of all of that. So if all events are isotropic and have the same energy as GW 170817, then Daksha will detect 3 per year. But if you have this Gaussian Phong model, then we will detect 12 per year. If we have an optimistic cocoon model, we will detect 18 per year. Okay, so we are taking that into account in this way by accounting for theoretical variations. But then we also did things like this, where we tried to be agnostic about it. We took a lot of models saying, here is a model assuming Kazan's model, there is Matiabullah's models. So a lot of these models were made by different groups, and those assumptions are being folded in. The last thing is that bias is not necessarily only towards optimism, it could also end up being towards pessimism. So for example, one of the things we are working on right now is if you take black hole mergers, 150914, the first ever detection actually had a weak 2.7 sigma candidate in Fermi. Okay, saying that there are potentially gamma rays, and there was it was a big party with people publishing papers as to how the black hole merger could have emitted gamma rays and so on around that time. But so we don't really think that they'll emit gamma rays, but the cost of searching is so low that right now one of my PhD students is doing a full search over all of Astrosat archival data corresponding to every single GW trigger ever received, saying that did we see anything? And based on that, we are putting constraints on luminosity functions of black holes. So we do try to be aware of potential biases to the extent that we can. And that is also when proposing a mission, for example, we don't propose it. EMGW could be the main science case, but we don't propose it unless we have a lot of other guaranteed science as such. All the GRB science is guaranteed because we have detected thousands of them. We know what all is going to happen and how we will do better.
Yeah, that's amazing answer. Thank you. But I just want to add to that, when the LIGO was funded, it was based on essentially 3 neutron star binaries. And we know that one of them will merge in, kind of 50 million years time or something like that. So yeah, so the payoff was pretty good. So yeah. Okay, so thank you very much for a wonderful talk. And yeah, we overshoot time, so that's perfectly all right. Thanks again. Hope to see you soon.
Thanks a lot, and I apologize again for not being able to come in person. I wish I were there. Thanks all.
Hello. Hello. Can you hear me?
Hi. Yes, I can hear you. Can you hear me as well?
Oh, yes, yes. Okay.
Okay, great.
5 minutes.
5 more minutes.
Yeah. Right. Yes. Can you see my slides already?
Yeah, perfect.
Perfect. Okay. So you have a break right now, right?
Yeah, once.
So what's currently going on? Do you have a coffee break at the moment?
Yes, sir.
I see. I see. All right. Yeah, I'm ready whenever you are. Yep.
Okay, okay.
So-
Island.
Yeah, a couple of more minutes, right? Okay. So I will mute myself now. You can just, and then I will unmute myself again when the talk starts.
Okay.
Hi, this is Gopu here. Can you hear us?
Hi. Yes, I can hear you. Hi, how's it going?
Yeah, not bad. Thank you very much for agreeing to give a presentation, kind of
Yeah.
colloquial here. So
Absolutely. Thank you so much for the invitation. I really appreciate it.
it's a pleasure. So, I said we had a long day, so people are kind of slowly gathering in. I mean, after the tea break, we will start maybe a few minutes. But yeah,
Yeah, that's fine. That's fine. Please take your time.
thank you. Kai, we will follow the German tradition of starting the seminar 5 minutes past the hour. So,
Yep, that's fine. Let's do it this way.
okay, welcome back. Now we will have a proper pulsar timing array talk. This is about nanohertz gravitational waves from cosmic strings by, Professor Kai Schmitz. He's from Münster. He moved recently to Münster from Geneva and has been very active in IPTA data analysis working group. And we look forward to getting updates from about nanohertz gravitational from cosmic string. Kai, please take it away.
Yeah, excellent. Thank you very much for the nice introduction and also for the invitation. So I'm really happy to have this opportunity here and, well, talk a bit about what you just heard, nanohertz gravitational waves from cosmic strings. Let's see, can I move to the next slide? Here we go. So I thought I would divide this talk basically into 3 main parts before then finally conclude. In the first part, I will review the exciting developments in the field of PTA searches for nanohertz gravitational waves during the last roughly 2 years and a half. And I guess for many, if not all of you, this will include a lot of material that you're very familiar with. After that introduction, in which I will tell you why we're actually interested in gravitational waves in this particular frequency regime, I will then turn to cosmic strings in the early universe as a particular source of primordial gravitational waves. And in those 2 parts, part number 2 and part number 3, I will first cover sort of the bread and butter version of cosmic strings, namely stable cosmic strings. And then I will talk a bit more about some slightly non-minimal scenario where those cosmic strings have a finite lifetime in the early universe and are actually metastable against the decay into monopoles, another type of cosmic defect in the context of grand unification. All right, so this is the plan for the next hour, roughly. And yes, let's start with the recent exciting developments in the field of PTA searches for gravitational waves. So now we can say that we might have caught the first glimpse of a stochastic gravitational wave background signal. We're still not quite there. I said that's why I am saying it might be a glimpse, and I put a question mark, so we have to be very careful. But certainly those developments have been very exciting. What we can say for sure is that now all of the ongoing PTA experiments have seen a strong evidence for a new stochastic red process in the latest pulsar timing data. This development has started with Nanograph, the North American PTA, that has presented its analysis of the most recent data set in September 2020. And you can see that here in the fit of the timing residuals, they find some excess power at low frequencies. This can be attributed to a common red process, which means that it is the same process among all the pulses in the PTA with the same spectral characteristics. And then you can see here the contributions at different frequencies. It is frequency dependent, which is why it's a red process, and particularly important at low frequencies. And also here in the right panel, you see the posteriors on the parameters of a simple power law fit through a number of frequency bands here, 5 or 30 frequency bands. After Nanograph had presented its first results, the Australians came along and presented basically, consistent results in this paper here. So also PPTA, the Parkes pulsar timing array collaboration, sees now excess noise at low frequencies, and the results are consistent with those obtained from Nanograph. Then a couple of months later, the Europeans showed their most recent results. This is based on 6 pulses in the latest EPTA data. And again, everything is consistent. For some reason, EPTA flips the axes here. So you see this is gamma versus A, not A versus gamma. But apart from this, it's consistent. And then at the beginning of last year, January 2022, the IPTA, the International Pulsar Timing Array, presented its most recent analysis based on, constituent data sets coming from the individual PTAs. And again, they find evidence for such a common red process, and it's consistent with the findings of the other PTAs. And of course, then in the future, we all hope that also the Indian PTA will contribute to those measurements and then find a signal that's consistent with what has been seen by those collaborations. So we have to be careful. It's not yet a detection, but we can also say that these observations are consistent with the interpretation in terms of gravitational waves. There is no showstopper here that would tell us that it cannot be gravitational waves. Of course, it's important to further validate this hypothesis, or to check that it's really of gravitational wave origin. And to do so, it's not enough to just look at sort of the autocorrelation of the timing residuals for individual pulses, but we actually have to perform a cross-correlation measurement across the sky. And we have to cross-correlate the timing residuals of individual pulses. And then we hope to see the characteristic quadrupole pattern in the sky predicted by general relativity. And this goes by the name of the Hellings and Downs curve. You can see it in the plot on the left-hand side, it's the blue curve, or the plot on the right-hand side where it's this dashed black curve. That's the prediction for the angular cross-correlation among the timing residuals of different pulses. And if we could confirm that, it would be very clear evidence for the gravitational wave origin of the signal. However, in the latest data releases, latest analyses, Nanograph 12.5, for instance, on the left-hand side, or Parkes PTA on the right-hand side, there is not yet, those analyses don't allow us yet to conclusively identify this Helix and Downs correlation. So what we can say for sure is that from those data sets here, we are not able to detect any monopole correlation. A monopole correlation would mean that there might be, for instance, an error in our reference clocks that we use to do the timing measurement. We also don't discover a dipole correlation. A dipole could, for instance, originate from errors in your coordinate system. For instance, if you get the position of the solar system barycenter wrong. And regarding the quadrupole correlations for gravitational waves, we simply have to conclude that the evidence at the moment is not yet conclusive. We need more data, more analyses, maybe more pulses to shrink the error bars and then get closer to this goal of finding evidence for the Helix and Downs correlations. However, for the rest of the talk, let's just assume that the signal we see in the PTA data is genuine and of gravitational wave origin. And then, of course, the all-important question is, what is the origin of where do those gravitational waves come from? On the astrophysical side of things, there is one particular interpretation that sticks out, and this is gravitational waves from inspiraling supermassive black hole binaries. those are systems, binaries of supermassive black holes that form after the mergers of entire galaxies. And you can see some pictures of the Hubble Space Telescope and other telescopes here that show basically systems after such a galaxy merger. They have those two active galactic nuclei here at the center. And while those are already supermassive black hole binaries in an early stage, they are still very far away from merger. But in principle, the idea is that such systems can enter a gravitational wave-driven regime at some point in their evolution, and then the orbit shrinks just because of the emission of gravitational waves until the merger eventually happens. And the superposition of gravitational waves from all those in-spiraling supermassive black hole binaries then gives rise to a stochastic background that also shows up in the nanohertz frequency band where we can do the measurement in terms of our PTAs. All right. So that's, of course, a very attractive possibility. And the big promise of those PTA measurements is that it will allow us to probe the physics of those supermassive black hole binary systems. However, at the moment, it's also important to note that on the theoretical side of things, the models and simulations are facing a few challenges. So here I just want to illustrate this in terms of two examples. On the left-hand side, you see basically a calculation of the signal strength in the PTA band based on an empirical population model for supermassive black hole binaries that's based on the observed quasar population. And well, in a sense, this is a 3-parameter model that crucially depends on this number here. This is the local density of black hole binaries in our cosmic neighborhood. And you can see that in order to fit the strength of the signal seen in the PTA data, we have to assume a local black hole binary density that is, in fact, a bit larger than what had previously been estimated, up to a factor 10 times larger compared to theoretical expectations from a while back. So if the PTA signal is due to merging supermassive black hole binaries, it might be that we have to assume or work with a larger number density of those objects than what we had believed previously. On the right-hand side here, you see a prediction of the gravitational wave spectrum in the nanohertz band based on a numerical simulation of galaxy evolution that's based on the Shark galaxy evolution model. And in here, in order to estimate or calculate the gravitational wave background, one has to make an assumption about the time delay between the galaxy merger and the black hole merger. This time delay is a quantity that typically ranges from a few 100 million years, maybe up to a billion years. But then if you choose that quantity, this parameter, the time delay, in this characteristic range, you also note that the signal struggles a bit to reach the observed amplitude. So here, in this case, it falls short of the amplitude. And again, you have to boost it by a factor up to order 10 to actually find agreement with the observed PTA signal. So at this point, this is just, these are just neutral statements, but we can now, of course, start to speculate about what that could actually mean. So it might tell us something about our models and simulations. It could just mean that our understanding of the history, the merger history, and the dynamics and the evolution of supermassive black hole binaries, that our understanding is not that good yet at the moment, and we just have to work a bit harder, and we have to improve our models, and we have to improve our simulations. And in a sense, we can now use the data from the PTA observations as an input to make progress in the field. So basically now, after years of theorizing about those systems, it can actually become sort of data-driven, and then we use PTA observations to feed them into our theoretical modeling. And at the end of the day, this will lead to an improved understanding, improved models, and everything is fine. That's one possibility. But those statements about the success of current models and simulations, might also tell us something about the signal. And it could be that the signal is not only due to merging supermassive black hole binaries, there might be also a secondary contribution. And that brings me to the topic of gravitational waves from the early universe, cosmological gravitational waves. So at the moment, one can say that it's indeed a viable possibility that the signal that we observe in the PTA data receives contributions not only from the supermassive black hole binaries, but there's a secondary contribution X, all right? And only the sum of the two can explain the full signal. Of course, you can also take a more extreme standpoint and say that everything we see in the PTA data must have a different origin. For some reason, the signal from the supermassive black hole binaries is too weak. Maybe it's still further down in the gravitational wave spectrum, suppressed by some factor, and everything we see right now has some other origin, maybe a primordial origin from the early universe. Now, if you take that idea seriously, then it tells you that those PTA observations actually provide us with a tool to probe the cosmology of the early universe and particle physics at very high energies. And this is, of course, a very exciting prospect, has attracted a lot of attention in the literature, and people have brought forward lots of different possible interpretations of the signal that we see in the PTA data right now. So here at the bottom of the slide, you can just see a completely incomplete list of ideas that have been put forward, cosmic strings, and we'll come to them later, but also lots of other possibilities. I will say a bit more about them in a second. So let me again emphasize the overwhelming reaction to the new developments in particular in the particle physics community. So this is the screenshot of the Inspire page of the Nanograph 2020 paper. And at the time I took the screenshot, the paper had already more than 400 citations. At the moment should be even more than this. And in those dozens and dozens, hundreds of papers, many authors have proposed dozens of possible interpretations of the PTA signal. All right, let me just summarize the main options here on one slide, and then we'll become a bit more specific and turn to cosmic strings. So what is the menu of BSM options on the table? So one possibility is good old gravitational waves, primordial gravitational waves from cosmic inflation. It has been known for a long time that cosmic inflation can also produce gravitational waves. However, the simplest models of inflation, standard single field slow roll inflation, have a red tilted frequency spectrum, and they are constrained by searches for the tensor to scalar ratio in the CMB. So in those vanilla scenarios, we do not expect an observable signal in the nanohertz range, but you can work with non-minimal models where maybe new degrees of freedom or other dynamics lead to a blue tilted gravitational wave spectrum, so that you actually reach the desired amplitude at nanohertz frequencies. And in such scenarios, you can then think about this interesting interplay between observations of the gravitational wave spectrum at nanohertz frequencies and the measurement of CMB observables on CMB scales. All right. A second possibility that has attracted a lot of attention and a lot of interest are cosmological phase transitions. We need to have a strong first order phase transition in the early universe to produce gravitational waves. This will not happen in the standard model, but we can think about new physics, BSM extensions, or for instance, the electroweak phase transition, or some kind of modified version of the QCD phase transition, and then there will be a gravitational wave signal from a cosmological phase transition. For the PTA measurements, we're particularly interested in a modified QCD phase transition that would take place at the right temperature scale of a few hundred MeV, and then give us a gravitational wave signal in the nanohertz range. Or it would be a phase transition in a dark sector where new degrees of freedom are involved in the phase transition. and we maybe only learn about those dynamics because of the gravitational wave signal. In any case, this scenario or these scenarios are complementary to laboratory searches that may also, or that can also probe modifications of the QCD phase diagram, or that look for new degrees of freedom in some kind of dark sector. All right. The next big class of possibilities are cosmic defects, and I will say more about them, much more in a few minutes. Here, some of the most attractive options are cosmic strings and domain walls, and as I will explain, this scenario establish a tight connection between PTAs, gravitational waves, particle physics, and in particular, grand unified theories, GUT models, GUT model building. But before we go there, let me mention one major class of models, and this is related to the scalar perturbations in cosmological perturbation theory. So here the idea is that in the early universe, maybe during inflation, you produce an enhanced scalar power spectrum on small scales, not at the CMB scales, because there we have measured the amplitude of the scalar perturbations, but on shorter scales, you have an enhanced scalar power spectrum. Those scalar perturbations re-enter the horizon after inflation, and that can lead to two things. One, they can source gravitational waves at second order in perturbation theory, and this would be then the signal that we see in the PTA band. And two, at the same time, the gravitational collapse of those enhanced scalar perturbations can lead to the production of primordial black holes. So this scalar-induced gravitational wave signal would be associated with the production of primordial black holes, and this opens up a window to another completely, absolutely rich phenomenology, because the PBHs, they can contribute to dark matter, they may be the seeds of supermassive black holes at the centers of galaxies, and so on and so forth. All right, so this was the review part on recent developments in PTA searches for gravitational waves, and why it is interesting to think about BSM options. Definitely, the supermassive black hole interpretation is exciting, and there will be much more progress on this in the future. But at the moment, it is definitely also very interesting to think about the BSM implications of the new signal. All right, and for the rest of the talk, now I want to focus on cosmic strings, and I would like to start with, as I said, bread and butter, standard, stable cosmic strings. But before we go there, let me introduce again defects in a slightly more general way. And I want to start with an example in condensed matter physics. That's a system that we all very well know from maybe still our undergrad studies. So we want to talk about a phase transition inside a ferromagnet, which takes place at a particular temperature, the Curie temperature. At high temperatures, above the Curie temperature, the system is in its symmetric phase, and all the elementary spins inside the ferromagnet are randomly distributed. There is no preferred direction, and the system actually is a paramagnet at that point. However, then you cool down your system below the Curie temperature, and the paramagnet turns into a ferromagnet. And at that point, the small magnetic dipoles align spontaneously and all point into a given direction due to the exchange interaction among those magnetic dipoles. But this will happen, or this preferred direction will only be chosen inside a finite volume. And in that volume, then you have a preferred direction, which means that you have spontaneous symmetry breaking. Now the translation and rotation and variance here inside the ferromagnet is spontaneously broken. So the phase transition leads to spontaneous symmetry breaking. And you also generate defects in the sense of magnetic domains. Now we have got one domain here in this little cartoon where the preferred direction is up, all right? But then a bit further away, there can be another domain where the magnetization points into some other direction. And the interface between those different magnetic domains are then referred to as the domain walls inside this ferromagnet after spontaneous symmetry breaking. And it turns out that those domain walls are stable. unless you apply an external force. Here in this case, it would be a magnetic field. All right, so this is a simple example from condensed matter physics. And there's a similar phenomenology in terms of phase transitions and symmetry breaking in the early universe. So let's take a look at that now. Now we're not going to talk about small magnetic dipoles. We're not going to talk about some magnetization as the order parameter, but we talk about scalar fields in the early universe. So we would just like to consider as a simple example spontaneous symmetry breaking in some n-dimensional scalar field space. All right. So let's take a bunch of scalar fields, phi 1, 2, 3, and so on up to phi n, and put them into such a vector here that lives in this n-dimensional field space. Then we take the entire vector and give the vector this type of scalar potential, which is the typical potential Mexican head type scalar potential for spontaneous symmetry breaking. And depending on the number of scalar fields, or depending on n, we can break different types of symmetries, and we can produce different types of topological defects. All right, so here in this general formulation, our scalar fields, they transform as a vector under some SON rotation, global or local symmetry. So we can gauge it, or we don't have to gauge it. Now let's talk about different numbers of scalar fields. If it is just one scalar field, like in the case of magnetization inside the ferromagnet, we can actually break some Z2 symmetry. This is what you can see in the cartoon here on the left-hand side. So inside the scalar potential, the field phi might be minus V, minus the vacuum expectation value on the left-hand side, and plus V, the other solution here of the equations of motion, plus V on the other side. These are the two different domains in the scalar field configuration, and they are connected by such a domain wall where phi is not minus V or plus V, but it continuously connects between the two, and there's this one region, this two-dimensional hypersurface in space where phi is 0, and this is the center, this is the core of the domain wall. All right. In 2 dimensions, we work with 2 scalar fields. And in that case, we break some SO2 symmetry, which is isomorphic to U1. All right. And then in position space, we find one sheet where the first scalar field vanishes. So this is maybe this one here. Then there are but also regions in position space where the second scalar field vanishes. Okay, and in principle, both fields undergo some random walk in position space, but then somewhere those sheets will intersect, and along the intersection, which is now this one-dimensional object here, the entire vector, all scalar fields vanish, and we are still in the symmetric phase of the old vacuum. So this then gives rise to this cosmic string in the 2D case. And we can go on in 3 dimensions. We can look at the the intersection of those 3 sheets. They will meet in one point, and that then describes the production of monopoles in the spontaneous breaking of SO3. All right, so at the technical level, those topological defects are solitonic solutions of the classical equations of motion for the Higgs field. So those scalar fields would be the Higgs field of the spontaneous symmetry breaking. If it's a local gauge symmetry, then there will also be special gauge field configurations around those objects. All right, and if you want to be even more formal, you can describe the formation of those objects in terms of the topology of the vacuum manifold after spontaneous symmetry breaking, which is why those defects are referred to as topological defects, and their stability is guaranteed by the topological properties of this vacuum manifold, and so on and so forth. So there's a whole zoo of composite defects. You can combine them into string wall networks. You can put monopoles on strings and so on. There are also non-topological defects, but I guess that's my one slide summary and everything you need to know for this talk. All right, so let's have a slightly closer look on cosmic strings. This is what we're going to be interested in right now for the rest of the talk. So as I said already, they are topological defects that originate from the spontaneous breaking of an SO2, but that's isomorphic to U1 symmetry, so spontaneous breaking of some U1 symmetry in the early universe. We can break a global or a local U1 symmetry. And one of the characteristic properties is that at the core, at the center of the string, the old vacuum still survives. Yeah, so this is where it remains preserved, even though in the bulk around it, everything has transitioned to the new vacuum after symmetry breaking. And in condensed matter, there's actually another analog or equivalent system for that. So in a sense, magnetic field vortices going through a superconductor can also be thought as a realization of the same phenomenon. All right. Yeah, maybe I should explain again the picture up here. So this is now a sketch of a Mexican head type scalar potential. Basically, the formula you've seen here in a two-dimensional field space. And in the case of a cosmic string, we can now see that a closed path here along the bottom of the Mexican head potential, the vacuum manifold, this path can be mapped onto such a closed path in position space. And if it goes once around here, it can enclose this region in space where the scalar field is actually still located here on top of the Mexican head potential. So phi vanishes along the green line. And again, this is where the old vacuum survives, even though the symmetry breaking process all around it. Okay, so there are a couple of important parameters to describe cosmic strings. The most important one is the cosmic string tension. So those cosmic strings carry energy because they live up here at the top of the Mexican head potential, which means they preserve that vacuum energy, which is no longer present here at the bottom of the Mexican head potential. And we quantify the string tension as its energy per unit length. This is the quantity mu, which has mass dimension 2. And if you multiply by Newton's constant here in natural units, if you multiply by Newton's constant, G times mu is a dimensionless quantity. Another important parameter is alpha. So those cosmic strings, they can form closed loops during the cosmological evolution. And alpha measures the size of those string loops at the time of formation in units of the Hubble radius. So again, alpha is a dimensionless quantity. All right, so now we know what cosmic strings are and how they belong to this class of cosmic defects. Now let's talk about the emission of gravitational waves from cosmic strings. And for this, first of all, I want to show to you the picture here on the left-hand side. This is a snapshot from a numerical simulation of a cosmic string network. And you can see that this cosmic string network, as it may have formed in the early universe, consists of two different types of objects. They are infinitely long strings, which are the strings you can really see here inside the simulation box. Those infinitely long strings are either really infinitely long, or they just correspond to closed loops, which are very large on scales larger than the Hubble radius at that time. And then there are also tiny loops, which look like these specks of dust here inside the simulation box. And those closed string loops, they are chopped off from intersecting long strings. The long strings intersect all the time, and they can interact with themselves, or they can interact in pairs, and those intercommutation events can lead to the formation of those string loops. What's important to note about this network here on the left-hand side is that it reaches what is called a scaling regime, which means that it begins to follow a self-similar evolution where a certain number of quantities just remain constant in the appropriate units. And in particular, the energy density stored in cosmic strings during the scaling regime will just go like the total energy density. So it will go like Hubble rate squared, which means that the energy density parameter of cosmic strings, omega cosmic strings, so basically the ratio of those two energy densities here, will remain a constant. So cosmic strings obtain a certain amount of energy or are responsible for a certain energy fraction of the entire energy budget, but they will never begin to dominate the energy budget and then lead to some kind of cosmological catastrophe. which means that they are safe in that sense, and that makes them an interesting type of cosmic defect. All right, so cosmic strings enter this scaling regime, and then during the scaling regime, we have the production of gravitational waves. And the gravitational waves mainly come from those small cosmic string loops. And how this happens, that's something you can see here on the right-hand side. So along the loop, certain features propagate. They are referred to as kinks and cusps. Here at kinks, the tangent vector just makes a jump. And cusps are these structures here. They propagate with the speed of light along the closed loop. And then the kinks and cusps emit bursts of gravitational waves into a certain solid angle. So you've got gravitational waves from cusps, kinks, and also kink-kink collisions. At the same time, the loop can also oscillate in its fundamental oscillation frequency just under its own tension, and there can be higher harmonic excitations of those oscillations. So all of this will produce gravitational waves. And then you look at the superposition of those gravitational waves from all the loops inside your network, and that together gives rise to a stochastic gravitational wave background. All right, and a few more technicalities. So there are different theoretical approaches as well to describe the evolution of cosmic strings. In the simplest case, you work with the Nambu-Goto action, where you forget about the field theory origin and you just treat the strings as infinitely thin. In this case, there are no Higgs or vector boson particles anymore. So particle emission is not even an option. You can also try to describe the string evolution or network evolution in terms of the abelian Higgs model, where you still try to account for the bosonic degrees of freedom, Higgs and vector boson fields. In that case, you may observe in some simulations observe that loops can decay very fast into those massive particles, which reduces the lifetime of the loops. There's some tension between those theoretical approaches here, which has not yet been settled. It has been an ongoing debate for many years. And it remains to be seen how the two approaches can actually be merged together. And on top of this, one can also think about non-minimal scenarios of cosmic strings. So here, these the simplest kind of strings that you can expect from the spontaneous breaking of a U1 symmetry. But as we will see, there can also be metastable strings, or strings can carry a current, and all of this can then be relevant for the gravitational wave phenomenology. All right, but before we go there, let me still point out the importance of cosmic strings in the context of grand unification. So the gravitational wave signal from cosmic strings can really basically build a bridge between cosmology and observation of gravitational waves on the one hand, and particle physics and grand unification on the other hand. And this is something you can see if you think about the possible embedding of your spontaneous symmetry breaking process into particle physics, in particular grand unified theory. So here I've taken this plot, this diagram from the first paper on the slide, and it shows to you how you can start with a big gauge symmetry, a big gauge group, SO10, and then consider different symmetry breaking patterns that eventually bring us down here to the gauge group of the standard model. And at the different stages of this symmetry breaking pattern, you can produce different types of cosmic defects, including cosmic strings, which are always these blue arrows here. So if you see a blue arrow, it means this could be realized as a phase transition in the early universe that gives rise to cosmic strings. And as soon as you embed the entire story into such a picture of grand unification, you can connect lots of different topics in particle physics. So here the underlying idea was to have a UV embedding of the seesaw mechanism, which is the extension of the standard model by right-handed neutrinos. So in that case, you can explain neutrino masses leptogenesis, cosmic strings, gravitational waves, and proton decay at the same time. You can study them at the same time. In particular, the idea here in those papers was that in the seesaw mechanism, you need Majorana masses for those right-handed neutrinos. Those masses can also be generated by kind of a Higgs-like mechanism in a spontaneous symmetry breaking process. And if there's such a symmetry breaking that generates the Majorana masses for the heavy neutrinos, that can at the same time also give rise to cosmic strings. All right, so let me point out one important example. It's basically the symmetry breaking starting here. This is the standard model gauge group enlarged by B minus L, where B minus L is baryon number minus lepton number. If we break that symmetry, it will generate the heavy masses for the right-handed neutrinos in the seesaw extension of the standard model. And this is basically just like one of those U1 symmetries I mentioned earlier when I defined cosmic strings for the first time. All right. But now also different interesting scenarios can actually take place. So for instance, if we break that gauge group, including U1B minus L, down here, then we just break it down to the pure standard model gauge group, SU3 cross SU2 cross U1. And the cosmic strings that we produce in this process will actually be metastable cosmic strings. Remember that I said the stability of the cosmic strings follows from the topology of the vacuum manifold and so on and so forth. Here in that case, the theory actually remembers that at the very fundamental level, it had not been such a U1 symmetry all the time. No, the theory remembers that at the most fundamental level, it was actually embedded in SO10. And then the breaking of SO10 down to the standard model, if you basically jump all the way from up here down here, that breaking does not involve cosmic strings. So if cosmic strings originate at some intermediate stage, they cannot be completely stable. And this is exactly what happens here. So in the last step, you do produce cosmic strings, but they are unstable against the generation of monopole, anti-monopole pairs that belong to the breaking of SO10. So now you can produce those SO10 monopoles on the cosmic strings. All right, so there's the strong connection between cosmic strings and grand unification. But now let's take a look at the data and then see how the gravitational wave spectrum can actually explain the PTA signal. This is from an analysis that we presented right after the nanograph paper had come out. So we calculate the gravitational wave spectrum from cosmic strings, and we fit the spectrum by sort of a power law ansatz in the nanohertz frequency range. This allows us to give a theoretical prediction of those spectral parameters, A and gamma. And our predictions are now shown here as those colorful points, colorful dots. It's the same data on both sides. On the left-hand side, the color code refers to the cosmic string tension. On the right-hand side, the color code refers to the loop size parameter alpha. And here we show that it's actually straightforward to populate the nanograph 1 and 2 sigma posteriors and on A and gamma. So that was very interesting at that time, because we found very good agreement with the nanograph result. But now we could go back to one of the earlier slides. We actually see that in the IPTA DR2 data, there's now a preference for smaller values of gamma and larger values of A. So the posteriors on A and gamma have shifted to the top left corner here, which makes it harder for cosmic strings to actually explain the PTA signal. And that is why it's very interesting to also consider metastable cosmic strings, where the gravitational wave spectrum is slightly different and where it's actually possible to go to this corner of parameter space. But before we talk about this, let me show you one last slide on the vanilla case. This is the gravitational wave spectrum from stable cosmic strings. You see 3 benchmark scenarios here, and they all meet by construction at the same point at a nanohertz frequency, roughly. So we can actually explain the nanograph signal for our cosmic string tension here in this ballpark, and a typical value for this loop size parameter. We can also scan our parameter space. Then we find those constraints on G mu and alpha. And basically every point in this parameter space corresponds to a gravitational wave spectrum that will be probed by future experiments. Not the ongoing experiments, but future experiments like LISA or third generation ground-based interferometers. So that's nice. Well, then another conclusion here is that if we want to go up to very large values of the cosmic string tension, so if we want to consider a symmetry breaking scale of the order of the GUT scale, grand unification, 10 to the 15, 10 to the 16 GeV, in our scan, we have to go to very small values of alpha. We have to consider very small loops. And that's something that you typically don't see in numerical simulations. So here in this case, it's not quite clear whether those cosmic strings would fit into a picture of grand unification. And also, with those predictions here, the extrapolated spectrum at higher frequencies is unfortunately too small for the second generation of interferometers. So the question is, how can we improve on this? And of course, the most important motivation for going beyond standard stable cosmic strings is that now with IPTA DR2, we actually don't want to be in this part of parameter space, but we want to be here in the top left corner, smaller values of gamma and larger values of A. And that's something we can achieve if we consider metastable cosmic strings. And this brings me to the third and last part of my talk. So yeah, just some of the basics, and then we can look at the prediction of the gravitational wave spectrum. So I mentioned already, those metastable cosmic strings, they are unstable against this monopole nucleation, and you can actually calculate or at least estimate the decay rate of such a cosmic string per unit string length. This has been worked out by those people here a long time ago. So you want to know what is the number of nucleation events per time interval and per length interval on the cosmic string loop. And this is given by this exponential expression here, which depends on two parameters. Mu is the cosmic string tension. It appears in the prefactor, but also in this kappa coefficient. And m is the mass of the monopole that appears here, okay? So mu is dimension 2, and m squared is also dimension 2. Kappa is a dimensionless parameter. Okay, so in such a case, the strings are not stable because they're not protected by the topology of the true vacuum manifold. They can decay on cosmological timescales. But that depends on the exponential suppression here. If the ratio of m to square root of mu, so the ratio basically of those two mass scales is some order 1 or order 10 number, then the exponential suppression will not be too strong, and we will see the decay on cosmological timescales. These are then true metastable strings. However, if there's a very large separation of scales between, let's say, SO10 breaking and U1 breaking, then this exponential suppression will be very strong, and the strings will not decay within the age of the universe. These are then basically quasi-stable cosmic strings. We can also distinguish different types of monopoles. The question is, those monopoles, do they still interact with some massless vector boson? Do they see some other type of radiation? Here I say, do they still carry or do not carry some unconfined flux? If they do carry some unconfined flux, then we actually have really monopoles and anti-monopoles. They can annihilate and release all the energy in the emission of massless gauge bosons. So then this will not contribute to the gravitational wave signal. But if they are completely neutral, by looking at them from the outside, they can only lose energy via the emission of gravitational waves. Then those string segments with two monopoles at the two ends will also contribute to the gravitational wave signal. All right, I've got one slide on our computational strategy, and then we can finally look at the results. We have to modify a bit the standard description of the cosmic string network. So I told you that when we looked at the simulation box, the network typically obtains or reaches this scaling regime with a self-similar evolution. But this reaches an end when long string segments begin to enter the horizon. These are then segments that already have a monopole on both ends. all right? And this is a type of object that you don't have in the standard case. When is that the case? Okay, so for this, we take our rate per time and per length, and we ask, when do segments with a length of the order of the horizon, when do nucleation events become relevant on segments of this length scale? So we replace the length by the Hubble radius here. And the time Ts is the end of the scaling regime that we want to solve for. But in standard cosmology, the Hubble time, the Hubble time basically just goes like time. So this turns into time squared. We can solve for this, and we find that the characteristic time at which those nucleation events become important on subhorizon scales is given by 1 over the square root of our decay rate. Okay, so now we can look into 2 different regimes. At early times, this effect is not yet relevant. This is more or less like the standard picture. We've got closed loops and long strings. The loops emit gravitational waves, and they can decay into segments, but this happens here on superhorizon scales and is not relevant for the production of gravitational waves inside a Hubble radius. However, at later times, at times larger than TS, nucleation events take place on subhorizon scales. So now also the loops can break apart and form segments on their own. And then we have got this population of segments coming from the long strings or from the loops that have broken up. And all of this can emit gravitational waves until the entire energy is dissipated and the network has disappeared. All right, so basically this new decay regime, this is new and changes the standard evolution that we otherwise have in the scaling regime. So our challenge now is to solve a set of partial integral differential equations to determine the loop and segment number densities, both in the first regime, this is more or less still standard, but also in the second regime where everything is quickly decaying. And then we match those solutions at this transition time. All right. Once we know the number density, yes.
Yeah.
Right. Perfect. Yeah, I'm getting to the end. So once we've got these number densities of loops and segments, we can integrate over all possible emission times of gravitational waves. For the experts in the audience, this is sort of the standard formula. So you've got the number density. These are the objects that emit gravitational waves. You have to put in some redshift factors, and then you weight this with an average power spectrum of gravitational waves that you expect from each of those objects, from each of those loops or segments. This is how the spectrum then looks like. So let's focus on the plot on the left-hand side first. The solid or the colorful lines is the new gravitational wave spectrum from metastable strings. And the gray dashed spectrum is the one from stable cosmic strings. And now we see if we basically choose the right decay time, we can suppress the gravitational wave spectrum just because the network decays and is no longer around at later times. In our analysis, we find that the gravitational wave spectrum is mostly dominated by the loops and not so much by the segments. There had been other statements in the literature before that. And we also study the spectral dependence here of the spectra of the gravitational wave signal. And well, our new treatment in terms of the exact number densities gives us the right scaling behavior here at low frequencies. For PTAs, the upshot of this analysis is that now because the network can decay, it has a finite lifetime, and we can suppress the signal in the PTA range. Okay, do we want to do this? Do we want to suppress the signal? Well, we can suppress it, and then we can increase the cosmic string tension to compensate for that. So that's what we're going to do. We basically make the network decay and has a finite lifetime, but then we can increase the cosmic string tension so that we get the right signal amplitude at the PTA frequencies. And this is now in a new part of parameter space where the cosmic strings actually have an energy scale or descend from an energy scale which is much closer to the scale of grand unification. So this now nicely fits into the picture of grand unification. And also because we now explain the signal by this rising slope or rising part of the gravitational wave spectrum, we can actually achieve a larger spectral index here in these units, which means a smaller gamma value, all right? So that means we can move closer to the part of parameter space that's preferred by the IPTA data. All right, so my time is almost up. I think I will skip this slide and I will come to the conclusions. So I talked about two different types of cosmic strings. I started with the vanilla scenario of stable cosmic strings. They are an attractive source of gravitational waves from the early universe. And we demonstrated that they allow to fit the nanograph 12.5-year data very well. But you could also see that IPTA DR2 prefers slightly smaller values of gamma. In terms of omega gravitational waves, this means a spectrum that's more steeply rising. And that leads to the question, okay, stable cosmic strings are still an interesting option. They remain on the table, but how about non-minimal alternatives? And that's why we talked about metastable cosmic strings. Actually, they have a better motivation. They're even more well motivated in the context of grand unification. You have to go to a certain part of parameter space where the cosmic strings decay just at the right time. If they decay too early, you will not see anything at PTA frequencies. If they decay too late, they will look just like stable cosmic strings. If you start with SO10 breaking, you also have some initial abundance of monopoles. This is the old monopole problem that was also one of the main motivations for inventing cosmic inflation. So if you first break SO10 at very high energies, you have to have a stage of inflation first to solve that monopole problem, but that's the same story as back in the 80s when people thought about the monopole problem. And well, once you make those assumptions, then you find some exciting predictions for PTA and interferometer measurements. We can then explain the PTA signal very well for values of the cosmic string tension that directly point to grand unification. So the next steps on our side will be to improve the numerical or to improve the theoretical description of a metastable string network, and especially numerically simulate the dynamics of such a network, and also to identify other signatures, like for instance, radiation from monopole anti-monopole annihilation, maybe the effect on CMB spectral distortions, and so on. And in closing, I would like to give you a brief outlook on some ongoing work. These are preliminary results, and then we hope that we will be able to make some significant progress now in the next few weeks. So I can imagine that there will be a paper on this still in spring, let's say March or April, but don't quote me on this. Anyway, so we were looking into this with more recent data sets. So we're looking, for instance, for stable and metastable cosmic strings with the IPTA DR2 data. This is the parameter space I showed to you, cosmic strings, cosmic string tension on one axis, and this decay parameter on the other axis. And we find a very nice fit of the signal in an interesting part of the parameter space. So this is ongoing. And then also in the context of the analysis of the nanograph 15-year data, we are searching for stable and metastable cosmic strings together with a whole range of other gravitational wave sources. So that's also going to come out later this year. Watch out for this. So stay tuned, and thank you very much for your attention.
Thank you very much, Kai, for a very detailed and somewhat technical, but one can follow nicely. So, questions and comments, Maura.
Yeah, thanks again for that talk. It was really great.
Thank you.
Lots of food for thought. But it was a really great overview. So I'm just thinking about our next nanograv result. And when we might be able to discriminate between cosmic strings and supermassive black hole binaries. And it seems like with just one spectrum, if we're only able to fit one spectral index and one amplitude to our data, it's going to be really impossible to discriminate for several years, because both models could be tweaked to fit the data. And so we really need two spectra, right? We need to distinguish two spectra in our data, which might be like 5 years from now, we'll be able to do that. So that's exciting. I think within 5 years, we might be able to say, there are for sure two different spectra with different amplitude spectral indices. But the other thing I'm thinking about is like the actual angular correlations, right? So like the actual, how well our background matches the Hellings and Downs curve once we have these angular correlations in the data. I think for, supermassive black hole binaries, we're always going to expect some degree of anisotropy, right? So if I think in our 15-year data set, if we do detect them, it's going to be really hard to characterize anisotropy. Maybe in the 17-year, we'll be able to say something significant about the anisotropy. And so I'm wondering, what are the predictions for the cosmic string anisotropy? Like how well, do we expect any deviations from the Hellings and Downs curve for cosmic strings? And might that look different than the expectations for supermassive black hole binaries? And might that give us like a handle in addition to just the spectrum?
Yeah, thank you very much for this question. I think these are all the important points and questions that you're raising. Of course, the important question is once we keep learning more about the signal we are seeing, how can we eventually discriminate between different origins of the signal? And first of all, the spectral shape is an important discriminator. For this, we have to, first of all, see some deviations from just a straight line in a log-log plot. So we have to see a deviation from a simple power law fit. With more data and more precision, hopefully it will become possible to say more about the actual spectral shape in the frequency band that we have access to. It will not continue to just look like one straight line, but then we can look maybe at the running of the spectral index and the running of the spectral index and things like this. So at the end of the day, spectral shape will be crucial in discriminating the different types of signal. And regarding the anisotropies, that's an extremely important point. I think it's fair to say that if we start to see some anisotropies in the near future, you mentioned the 17-year data set, it will be very likely that this has some astrophysical origin because most cosmological sources of gravitational waves will not have anisotropies at a very large level. In most cases, they will just inherit anisotropies stemming from primordial density fluctuations in the early universe from the time when those sources were active or when the cosmic strings were produced. So here in the case of cosmic strings, they will inherit density of perturbations in the configuration of the network coming from primordial scalar perturbations. This will be at a very small level. We will not be able to measure this in the 17-year data set. So large anisotropies in the near future will definitely point towards the astrophysical interpretation. And another point, specific for cosmic strings here is that it's one of those gravitational wave signals that has the nice and very welcome property that it extends to higher frequencies. For many other sources, that's not the case. For instance, the supermassive black hole binaries, they will reach some cutoff frequency here. And then, of course, at higher frequencies, you can look for black holes in other mass ranges. But anyway, you can also think about gravitational waves from a phase transition. A phase transition will give you a bump, a peak in the gravitational wave spectrum. So if it's located here at nanohertz frequencies, the same phase transition will not give you a signal at, let's say, millihertz or millihertz frequencies or in the audio band, which is probed by the ground-based interferometers. And cosmic strings are special in the sense that because of this nice scaling regime in the early universe, this self-similar evolution, the cosmic string spectrum can actually stretch across this large range of frequencies. So that could also lead to some, let's say, circumstantial or complementary information. If in the future we should also detect a stochastic gravitational wave background just at the right amplitude, for instance, with LISA or third-generation ground-based interferometers, where it matches with this prediction here, this could also give more credence to the possibility of cosmic strings.
Just changing tracks a little bit. So about 15 years ago, there was a lensing candidate which people considered as a strong candidate for a cosmic string. So I guess what happened to that? Probably it's gone away since we don't hear about it. And just more general question, can you comment about the prospects for detecting such candidates through lensing from Vera Rubin and other next generation surveys?
Oh, wow. Yeah, that's a very good question. I'm not sure whether I'm really qualified to answer it. I'm more like an early universe person. And I should also emphasize that the gravitational wave spectrum that we see here in this plot, this is our theoretical prediction, or the gravitational wave spectrum that we, that may show up here in the PTA data. These are really gravitational waves from the early universe. So those cosmic strings are produced within the first fraction of a second after the Big Bang. They start to evolve in this characteristic manner that I just described. They enter this scaling regime and they continuously produce gravitational waves. But this is a primordial gravitational wave background, which is then propagated towards us for 13.8 billion years. And this is what people often refer to or often mean when they talk about cosmic gravitational waves from cosmic strings. Another possibility is that we think about cosmic strings that are still around in our present day universe. There are also possibilities for that. If you just follow the standard evolution of the network, then you will conclude that the number of cosmic strings in our universe today is very small. So it's not that likely that any of those cosmic strings is particularly close to us. But you can make some extra assumptions. You can think about cosmic strings that live in the centers of galaxies or things like that. And then you can actually do a completely different search. So here we're looking for a stochastic background from the early universe. And that different search would be to look for isolated gravitational wave bursts in the present universe that come from some cosmic strings in our cosmic neighborhood, maybe within, I don't know, the Virgo supercluster or something like this, in the sense that there is a cosmic strings somewhere close by. It gives us a burst of gravitational waves, and we can see this in our data. So these are two different things. I don't know much about the setup that you just described, gravitational or lensing actually from individual cosmic strings. But if you search for gravitational wave bursts, that's another possibility to look for cosmic strings in our neighborhood, in our cosmic neighborhood.
So, Kai, I have a follow-up questions. So this is about, as you correctly pointed out, isolated events involving cosmic strings. I mean, for example, if you kind of mentioned about, kind of oscillating cosmic loops characterized by a G mu and an alpha, right? It has a clean spectrum that gives you the, kind of burst radiation, right? So, so we are now thinking about there's another way astrophysically such bursts can be obtained. So this is just a hyperbolic encounters or supermassive black hole. It's also in the neighborhood. I mean, but it may be a good idea to kind of make comparisons how these, two signals look in a parameter space where we can actually think about. This is something I will come back to you. And interesting aspect will be if you are considering hyperbolic encounters, it comes with a memory. I don't remember cosmic strings, some papers by Thibault and others. I don't remember the cosmic string kind of vibration giving you a memory, right? There's no memory in that, if I remember correctly.
That's a good question. I don't know. I mean, I know that there are these searches for bursts with memory, right? I mean, we're also doing this with a nanograph data. That's a good question. I will have to look into this. I'm not entirely sure. But I mean, you're raising a very good point. Of course, there are other sources of such gravitational wave bursts. And then it's very interesting to, you want to have a prediction of the waveform as accurate as possible, right? And you want to see whether you can actually, whether you are sensitive to differences in those waveforms. So you would like to see what is the signal expected from a hyperbolic encounter, and how can I distinguish, how can I tell this apart from a signal caused by a gravitational wave burst from a cosmic string?
That's right. That's right. I think we should take it offline, but this is something I will come back to you. Yeah. So I have another. Yeah. I mean, so another question was about when you are talking about the sub-horizon,
Mhm.
you know, cosmic string collisions that you kind of unstable.
Mhm.
So I mean, they may have implication for cosmic microwave background and those,
Mhm.
so people, are there investigation on that direction, or this is too early?
Yeah, that's an excellent point. I mean, if you know somebody who would like to work on this, we should also talk. I mean, I think at the moment the literature on metastable strings is not too large at the moment. I mean, there are a couple of papers, and I mean, of course, people are interested in the gravitational wave spectrum. That's also what I mean. Here we got some PTA people on this paper. And yeah, I mean, I also worked on this myself, the gravitational wave spectrum from metastable cosmic strings. But on my to-do list, I've got this question: what are other observable signatures? So one question, for instance, is if those cosmic strings break apart and they begin to oscillate, under which conditions can they actually form primordial black holes? It might be that you start this oscillation, and then at some point, enough energy or enough mass is contained within its own Schwarzschild radius. Or I mean, that point would be Schwarzschild radius, but then everything is concentrated within a small volume, and that will just collapse and form a primordial black hole. So those oscillating pieces of string might, under certain circumstances, lead to the production of primordial black holes. That's one thing. The second possibility is that those monopoles still interact with some massless gauge field. At the end of the day, this could be the photon after all the symmetries are broken at the end of the symmetry breaking pattern. So those monopoles, anti-monopoles, can interact with photons, and then the annihilation could basically inject energy into the photon bath, maybe at just the right moment of time, and maybe induce some spectral distortions, to the photon phase space density that cannot be washed out anymore by Compton scattering or something like this, and that might give rise to spectral distortions of the CMB. Another interesting observable for future observations.
Oh, that's very interesting.
That's more like a question than an answer from my side. Yeah. So my question to you and everybody else is, what can we learn about CMB spectral distortions from those objects? And yeah, that's something that needs to be investigated further.
Yeah, I mean, so we have colleagues. Maybe we should. I will put you in touch with someone who's a colleague of mine back in Mumbai.
Nice.
So it's a kind of things to talk about. Yes. So
sounds good.
Great.
Let's do that.
Any further questions, comments? If not, let's thank Kai for a fantastic talk and keep in touch.
Yeah, absolutely. Thank you so much. Yeah. Enjoy the rest of the meeting. Thank you. Bye-bye.
Thank you. Bye. It's too late. So, yeah.
No. I'm still around. Is there another question?
No. We were thinking whether are there any questions from the Zoom audience? Doesn't seem to be like that. So.
I don't see anything in the chat.
Yeah. Thank you once again.
Okay.
We'll catch you.
Okay. Thank you. Yeah. Bye-bye. Thank you. Thank you so much.
Bye-bye.
Saying that you needed to put that in. Shall I get it? Yeah, so because participants have both classes. Today he has, so regularly he has like Monday to so during the session we cannot use it. I'm using ours.
So those who are in Zoom, Ramesh, Susmita, we are going to close now.
Tomorrow night.
Yeah, tomorrow 9:30 we can catch you guys later. So bye.